Welcome to breadboarding. This is a picture of the CGA card where we left it last time. So we spent quite a bit of time wiring up all of the output logic here that sends all the attributes and the characters out to the VGA connector over here. And in this video we're going to be looking at wiring up more of the video RAM and the CPU bus to the card. So this is video 55 in the Breadboard 8088 PC series, and this is a 10th part of our CGA video controller. So this is all part of the overall plan to produce a breadboard PC capable of running early versions of Windows. So we'll hopefully be able to run version 1, version 2 of Windows soon. We need to complete the CGA video controller in order to do that. So this is the block diagram where we left the project in the last video. So we've wired up all of this green stuff here. So a lot of this is to do with the interpreting the attribute values and the character values and sending those out to the digital analog converter for VGA output here. We also wired up the control and color registers as well at this point in time. Now what we're going to do now is to add in the video RAM here. Now the CGA card only could access 16 kilobytes of video RAM. The chip we've got here is 32K, but we're only going to be using the first 16K of it for now. Now around the video RAM, because this is not dual port video RAM like we were able to use in the monochrome display adapter, then in fact we need to add more buffers and latches around this. So this increases the chip count around the RAM here quite a bit. We're also going to be wiring in the status register, and we also need to add an additional latch here to feed the high resolution 2-color raster bits into the shift register here. And we also need to put logic in place to turn the character generator ROM off when we're outputting graphics, and to turn the graphics off when we're outputting characters. Now in the earlier videos what we've been doing is taking the address lines out of the CRTC and just been feeding those into the attribute and the character generator just to generate some test data. But what we're going to be doing now is, once we've got the video RAM hooked up and it's working, then we should be able to generate a more meaningful test output. Now when in the text mode, the lowest bit of the video RAM, bit 0 of the address, this was using the dot clock divided by 8, or also sometimes known as a character clock, or the QC. There's various names we've called it by. And this varies between 0 and 1 within each character. And so it can be used to actually switch between the attribute byte and the character value byte. Now when we go into high-res graphics and medium-res graphics, then in fact the way how the CGA card organised the RAM is the 16K was organised into 2 blocks of 8K. The even lines used row address or raster address value of 0, and the odd lines had a raster address value of 1. So effectively alternating lines in the memory map actually were 8K apart. So that's something we need to do to make sure that we maintain CGA compatibility. So to make the CRTC address mapping a little clearer, I use this sort of chart really to help clarify this. So on the left hand side here we can see the video RAM addresses for 32K. There are 15 address lines going from VA0 to VA14, so it's 0 indexed. Now when it comes to the CPU mapping is fairly straightforward. We can see here that for both the character-based 2-color high-res graphics and 4-color medium-res graphics, that in fact the mapping is 0 to 0, 1 to 1, all the way down to 13 to 13. So that's fairly straightforward. Where things get a little bit trickier when we look at the CRTC mapping. So for the character text-based mode, then the first bit is in fact this character attribute QC clock. So this toggles between 0 and 1 for each character, allowing us to have 2 bytes for each character, 1 for the attribute and 1 for the actual character value itself. And then we can see then that MA0 is mapped to VA1 all the way down to 5 going to 6, and then on the upper address lines there 6 goes to 7 all the way down to 12 going to 13. Then for the graphics modes, for the CRTC 2-color and CRTC 4-color, you can see that VA0 is mapped to MA0 all the way down to MA6, and then similarly VA7 to MA7 and VA12 all the way down to MA12. Where they differ really is that the VA13 is mapped to the raster address 1. So raster address 1 really just divides this up into 2 blocks of 8K. Even lines where RA1 is 0 will be in the lower 8K, and the odd lines will be in the upper 8K. And if we have a look over here, this is where we've got our definition for our two CRTC address multiplexer PLDs. So the first one, we've got the 7 output address lines, and then we've got combinations for the text mode. We're actually taking QC, or character attribute, down to MA5, whereas for the graphics mode we're taking MA0 to MA6, so that depends on the value of the graphics mode there. And then for the text mode over here, the mapping will be VA7 to 6 all the way up to 13 to 12, and then 0 will be going to VA14. Where in graphics mode, then these outputs here will be mapped to these values here. So if we take a look at the PLD configuration files, it's probably easier to see these mappings there. So this is the first PLD for the lower address line. So you can see here we've got VA0 to VA6 and all the inputs there. And down the bottom here, really, this is where we've got our mapping. So A0 in character mode, so inverted graph, is the character attribute Q3. Otherwise it's just MA0. And then we can see here we've just got 0 to 1 down to 5 to 6 for the character mode, and then these numbers just match on the graphics mode. So that's fairly simple for the lower bits. If we look at the upper bits, so we've got VA7 to VA14 and all the inputs over here, and the mapping there all the way up to 13 to 12 for the text mode. And then for graphics mode, we've got the 1 to 1, 7 to 7, all the way up to 12 to 12, but then 13 is the raster address 1. So that's fairly straightforward. If we have a look at the other logic PLDs at the moment, this first one here is actually providing the address bus output enables and latch signals for the high-res graphics 2-color latch, and also the buffer for the data bus buffer. So if we have a look at some of the schematics for the data bus buffer control, this is the main CPU PC data bus. We've got the direction control here and this chip enable data gate. So the buffer direction is fairly straightforward. Basically A to B is when dir equals 1, so that's effectively CPU write. So A to B is CPU write, and reading is B to A. So the logic down here basically says that if we're reading memory or reading IO or doing DMA, which we'll ignore DMA for the moment, DER goes low when we're reading IO. So that's one part of the signals. Then the data gate enable basically says if we're accessing the video RAM or we're actually accessing any of the IO ports during an IO read or an IO write operation, then we also enable it. So the rules down the bottom here. So our buffer basically says we enable the buffer when we're doing any CGA IO and there's IO read or IO write, or we're accessing the CGA RAM. And then direction basically says we'll set the direction to be 0 when we're reading either RAM or IO. And then the other values here for the character generator enable will be disabled when we're in black and white mode, the 640 2-color graphics, and the 2-color graphics latch will be enabled when we're in 640 BW mode. CRTC video address multiplexers, they are going to be enabled when we're not accessing the video RAM, and the CPU address bus latches buffers, they will be enabled when we're accessing the CGA RAM. Again, all these things are defined with sort of positive logic. Because a lot of these pins are active low, what we do is include the invert on the mapping, so it means we only have to worry about the true values during all these rules and things, and then the inverted side of things for active low is actually handled by the pin mapping. Then we've got the CPU address bus latch enable, so when this is high, this will actually mean that the CPU address bus is just passed straight through to the video RAM. At some point in time, we may make use of the latching so that we can actually update the video RAM in a period where the CRTC is not using the RAM, so we can get rid of any potential video snow. So this is what this comment is down here. Then our other logic here is more to do with control of the 74LS646. So this is like a bidirectional buffer stroke dual latch. And again, we're not going to be using the latching side of things at the moment, but we might be able to use those to get rid of CGA snow in the future. But basically this is just defining the rules. Then again, to enable the video RAM output enable is whenever the CRTC is accessing RAM, it will always be enabled. And whenever we're reading the CGA RAM, we're only going to be write enabling when we've got the CGA RAM enabled and we're trying to write. The direction is again worked out in a similar way. And then we can see that select AB and select BA values are permanently enabled to pass through the data, so not to do any latching, and the clocks again are similarly disabled. We may want to change these if we want to eliminate CGA snow in a future video. And finally, the output enable of this buffer stroke latch will be when we've got CGA RAM and we're either reading or writing the memory. So we're going to be programming all those rules in a little while. We're just going to have a look at the schematic diagram first to see what changes we're going to be making. So the overall diagram, it's getting quite big now. Now in the previous video we were really looking at all of the chips on this side of the board, a few around here, and what we're going to be looking at during this video is really all this lot down here, and in particular the video RAM down here. There's a number of address buffers from the CRTC, latches and buffers from the CPU address bus. Then we've got a buffer chip here, buffer stroke latch chip here, which can be used for the CPU to access the data here. Some control logic here to manage the signals around here. We've got some more control logic up here, which then controls the data buffer, where we're buffering the main CPU data bus to the rest of the board here. And then we've also got the status register here, the character latch that takes the data out of the video RAM and feeds it into the character generator ROM here. And we've also got the high resolution 640 by 200 graphics latch here, which again takes the video RAM and feeds it into the shift register over here. So to start with, what we're going to do is to program the PLD. So we've got this one, which are the two logic PLDs, and then two address multiplexers. So we're going to program those first, then we're going to plug it all in and wire in all of the power rails and decoupling capacitors first, and then we'll start to go through the individual chips and actually wire them up. So first of all, taking out CGA Logic 1 PLD and program that. Put that back and then get CGA Logic 2. So these are the control logic for the various latches and things we'll be putting in a bit. And then there's the first of the two address multiplexers that is used to switch between the different graphics and character modes from the CRTC addresses. Now we're going to start wiring in all of the power rails. So in addition to each of the ground rails there, we also put a decoupling capacitor in. So this stops a problem called ground bounce, which can cause interference on the circuit. So generally you want to put a 0.1 microfarad capacitor pretty close to the ground rail of most chips. Then wire up the remaining chips down the bottom of the board there, and then check all that off on the schematic. So now we're going to need to wire in various control lines. Now we're going to be taking those from other parts of the board, so in particular around the bus controller, and we're also going to wire them up towards the top of the board up here as well. So because of where the connections are, it's going to be easier to wire them in down the bottom here. So just going to start wiring in the CGA RAM enable, memory read and memory write, then the IO read and the IO write. So we're going to wire the CGA RAM enable up to the top there, along with the memory read, memory write. Put in the CGA IO and also the IO read and IO write there. Check those off. So now we're going to wire up the control signals for the buffer latch. Just tie those cables down a bit. So this is the various control signals for our 74LS 646 buffer stroke latch. And then the video output enable and the video read write. Now we're going to wire up the logic one of all the various chips. So we're going to first of all wire in the 640 by 2 color control line. Then we're putting in the buffer output enable for the data bus buffer and the direction. Then the chip enable for the character generator, and the output enable for the 640 2-color mode, and the output enable for the CRTC multiplexers, and the CPU address latch output enable. So now we're going to wire in the status register. So a number of the inputs to the status register are either tied to 5 volts, tied to ground, or come from the vertical sync or the display enable blank signal, and then that's the latch. Okay, so we finished wiring up the status register there, so let's just have a look at some of the values there. So we can see that A0 or D0 as it will be when we hook it up to the data bus is the blank display enable, A1 is tied to ground, A2 is tied to 5 volts, A3 is our VSync delay, so this is going all the way off to the vertical sync output on the VGA connector there, and then the other lines are actually tied to 5 volts. So let's have a look at the status register documentation just to see what all that means. Here's some information from earlier videos about the CGA status register. You can see here that bit 0, 1 indicates that the regen buffer memory access can be made without interfering with display. That basically means is the inverted display enable, which effectively is true when it's blank. Then this means we can update the video RAM without any CGA snow effect that we'll probably see a little bit later. Down the bottom here we have the 1 indicates the raster is in vertical retrace mode. So this basically means vertical sync is ongoing. So again, that's true during the vertical blanking period, which is generally going to be a lot longer than the horizontal sync period. Now the other 2 bits are related to the light pen. Now we're not going to bother with the light pen, but bit 1 we're going to tie to ground because a 1 indicates that there's output from the light pen's trigger, so we don't really want anything to think the light pen's being used. And then the light pen switch 0 indicates that the switch is on, so we're going to tie that to 5 volts or a 1 there. So bit 2 is going to be tied to 1, bit 1 tied to ground. So I've taken some of the DuPont cables we're using for testing, and now we're going to be wiring up the 640 2-color graphics latch. So when the character generator ROM is disabled, then the data comes from this latch into the shift register up there, all 8 lines coming out of the graphics latch there. Okay, so we've pretty much finished wiring up the board. There were just a few things that I added when it was off camera. I didn't actually record these, so there were some clock signals to this latch down here and another clock signal going to this one. So this was the 640 by 200 2-color graphics latch, and it has a clock for the character, as a character latch clock here. And then there's also the RA1 from the raster address over here going into here, and the graph control signal comes in from there. So those are 2 things I wired up, which I didn't actually have videoed, unfortunately. So now what we're going to need to do is to wire in all the remaining DuPont cables. There's an awful lot of bus connections around here. So if we have a look at the KiCad schematic, so we've got a number of buses coming in here. So if we highlight the data bus, so this is the main CPU data bus, comes into the buffer here, and then on the other side of the buffer we've got these two connected, and then from here we need to make sure we connect over to the digital analog converter, and this is still connected to the CRTC, the colour latch here, and the control register. So hopefully if we get those wired in, then that should be okay. Then there's the address lines. So the address lines are coming in the lower A0 to A7 down the bottom here, and then A8 to A15, although we're not using A15 at the moment over here. So that needs to be wired in there, and then we also then need to wire in the lines up here, because I've removed those cables so that we can wire it in again. So that'll be the address lines. Then we're going to have the video address lines, and this gets a little bit tricky in that the inputs to the video address lines are coming from MA0 to MA6, but MA6 actually maps into both these chips. So there's an overlap there, and MA6 to MA12 goes into this top one. And we've got another gotcha here in that the outputs of this one here is VA8 to VA14, but this one here does actually output VA7 to VA14, so you have to be a bit careful. So note the offset that we're dealing with an 8-way and 7-way here, so we just need to be a bit careful wiring these things up. And I've also done a comment in here that we are going to be using 7-way DuPont cables for these connections from here to here. So that's another gotcha. Then we've got the video data. So the video data is coming out of the 0, 1 and 2 pins there, and the 3 to 7 there, and that needs to go off to this side of the video RAM buffer latch. This is the 74LS 646 buffer latch chip we've got, and also to the output side over here. In fact, I just realized that this chip is actually on the diagram is the wrong way around. It's correct on the board, but when I put it in here it's not quite the right way around, so I'm just going to switch that over. Okay, so just switch those around, just took a few minutes to do that. So now if we look at the video data bus here, so this has got to be connected up to the output of the video RAM there. If we look at, say, the D0, we can see it goes into the buffer latch there on this side. The other side is the data bus, main CPU data bus, and then video data goes down here. We also need to then hook up the video data, needs to go up to these two latches up here as well. And data bus also needs to come down to the video RAM buffer latch, so we need to worry about that. So what I'm going to do, I've got something like 20 odd DuPont cables, so I'm going to wire those up. I will speak over, but we'll come back once we've wired all of the DuPont cables. It is going to look quite messy once we've finished because the cables were going everywhere, and I do have also the data bus. So I've got the address bus, data bus, and the upper and lower address lines down the bottom here, which will be plugging in down the bottom of the board once we're done. So we're just going to do the CRTC address lines into the two multiplexers. So these are 7-way cables and they do overlap on the same address line on the CRTC there. Then we go wiring the data bus side of these two lots of chips here. In fact, the top one there was put on the wrong side, which I'll correct in a minute. Now we've got the video address lines there. So the video address lines for the lower 7 or 8 bits were done off screen. And this is wiring in the video data output into the buffer there. And then we're taking the video data into the attribute latch there. Now I just corrected the wiring there for the data bus there. So now we're going to be connecting the data for the video RAM buffer up to the status register there. Now we're going to wire up the video data coming out of there up to the 640 graphics latch and the character latch. So now we're wiring in the upper video address lines into the video RAM there from the multiplexer. Now taking the data bus over to the video DAC there, which also goes to the CRTC. Now need to wire up the character latch output into the address lines for the character generator ROM. Now we're going to be wiring up the address bus from the input there from the CPU up into the top of the board with the decoder for the lower address lines and the upper address lines. Now we're going to wire in the CPU data bus, and now wire in the lower address lines from the CPU and the upper address lines from the CPU. Okay, so we've finished wiring everything up, so hopefully that's everything. I'll go over the diagrams and just check again before I actually start doing any testing. So let's just move the camera a little bit higher up so we can see the whole board now. So you can see that all of the DuPont cables, they certainly make wiring everything up a lot easier. If you think there's a 20 plus DuPont cables here, that would be 20 times 8. So there'd be an awful lot of individual wires and connections we'd have to do there. So it certainly simplifies things quite a bit. So just now need to update the test software. So this is the same sort of software we were using in the last video. I've just updated it to enable some of the test pattern output. So it's doing all the same things with the palettes and things, but now it's actually outputting a test pattern that we've used in some of the earlier videos in the series. I'll then wait for a key. I think it will be blink enabled on the first time through, and then the next time through it will actually turn blink off. So I'll just need to assemble that, load that, and then we'll try and run up the CGA card and see whether we get any output from it. So let's assemble the test program. So we're using NASM here from the command line. Now I'm just going to turn on the Breadboard BC, and we just need to download the test program here. So you can see here we've got CGA Test 5.srec. Now I just need to set the segment for this to be loaded into, put it into load, and then we're just going to send this. Okay, so that's all finished. Now I have already run this a few times and I had a few issues that I needed to fix, just to go through a couple of those. So I'd forgotten the output enable on the character latch, so this just needed to be tied to ground. So it's one of the things that I found when I was checking through the schematic, and that just meant that there wasn't any character output, so we weren't getting any characters coming out. I also found that although I'd wired up the output enable on these two PLD multiplexer chips, the actual configuration in the PLD didn't have the output enabled on all of these outputs, and so what was happening is when the CPU was trying to write to the RAM and the addresses were from the CPU, then also the CRTC addresses were confusing things, which was a little bit tricky to get to the bottom of, but that's all been resolved now. And there are a few other issues. So for example, I realised once I did a bit of debugging that I need to change the AND in this condition to an OR. I've missed out an exclamation mark on this output here for the output enable for the 74LS646. These two multiplexer PLDs, I had the output enable on the diagrams on the schematic, but I didn't actually have the pin identified, and I also needed to just set the output enable, so that just meant that this wasn't fighting with the CPU addresses. And again, similar for this one, so we just have to put in the output enable and then put terms for that. So all those have been programmed, so now we're in a position to be able to have a look at the board, and I'll do it with the VGA screen in the right hand side there. So I'm going to do now, once this runs up, first of all, it's just going to clear the screen, and then there's a couple of test patterns on the character mode. I'm not going to test the graphics in this video, we'll do that in the next one. So I'm just going to run up the test program, and you may just be able to see that we've got a cursor at the top left hand side, and you can see there's a little bit of snow interference on there. Now I'm just going to press key here and we'll get the test pattern. Let's make that a bit bigger. So you can see that we've got our numbers going all the way across the top and down the bottom. There's one or two stray characters appear here, And at the moment we've got the blink is disabled at the moment, and so we've got actually the full range of 16 colours for the background. So you'll see at the bottom here, the background towards the bottom here is lighter than the background in the sort of top sort of 10 rows here. And when I press the key, what it's going to do is to turn on the blink enable, and you'll see that all of the backgrounds will then become the same and you'll have the blinking. So now you can see that the background on the lower half where it's blinking there is now the same colour as above, and you can sort of see there's a few more characters have kind of got updated for some reason. So I think there's a few timing issues that I need to look into, but the basics of the card are working okay. And you can see down the bottom on row 19 here we've got the black, blue and all the other colours going along there all the way up to white. Now that we've got the data buffering for the CGA card, then the issues I was having with updating the palette digital analog converter seem to have gone. Now if I keep on pressing the key, you'll see there's a bit of interference there. So this is the CGA snow that I mentioned, and that's because at the moment we're not actually trying to coordinate between the CPU access and the CRTC access. And you can see there's a few stray characters appearing in the black areas here from time to time. So there's probably a little bit of timing issues to do with when the CPU and the CRTC are going in and out of sync or phase with each other. You can see there's a few of the numbers down the left hand and right hand side here have also disappeared. So there's a few issues that need to continue to look into, but what I'll do is leave that to the next video, and I'll just run up the original test pattern again. So we'll just run the program again, just a little bit nicer to look at. So there we have it. We've got the basic CGA card working. The text mode with 16 colours is all working okay there. There's a bit of interference, but we'll look into that over the coming video. What I'm going to do in the next video is to change the BIOS so that it knows about the CGA card. We'll need to do a bit of configuration also on the board to make it choose CGA rather than the monochrome display adapter. And then I'm going to run up some basic programs to test the various graphics modes. So we'll be looking at the graphics mode and see if we can run any of the other CGA test programs as well. So if you don't want to miss out on future videos, then please hit subscribe, and if you found the content interesting, please hit like. It just helps to make the videos available to more people. Thanks for watching.